Okay, so today we're going to look into the active operation framework. So there are several aspects that we are going to see, but first let's see some context of problem details that solving and which approach is followed. So it's all about model synchronization. And model synchronization is about maintaining a kind of correspondence between a set of models. This is a significant unsolved issue in the MD community. There are some approaches, of course, but there are no real killer apps for this. Of course, the active operation framework is not also the miraculous solution, but it provides some interesting advantages that we're going to see today. So, synchronization can be about relations within a model, and one of the most practical applications is derived features. And it can be between the models, inter-models, and then you can have applications such as transformation. So the solution proposed by the active operations framework has been developed to synchronize models. It is currently within Papyrus on Eclipse. Currently, it's still on a development branch, which is listed here. Actually, if I click, you should be able to see, yes. So here you see on this branch, we have in extra plugins, AOS, we have these 3 plugins. So the core plugin is for the basic functionality. The EMS plugin is for everything that's EMS specific. And there are some helpers in the long specific. Additionally, there are some test plugins which are in another folder of the Git repository. And as we will mention several times during the presentation, we already have a user, Christian Damus, is using the active operation frameworks to do some very interesting things. So I hope he will not mind that I will reuse some of his videos to show you what we can do with this, and maybe he can comment if it's appropriate. So that's fine by me. Okay. Thank you. So I have also some links to your project, Christian, but they come later. So AOS defines some incremental algorithms for operations which are very similar to OTL operations on collections, which are also similar to the collections that you have in OCL. This is not really unexpected, because actually what you have in OCL is very common in functional languages, although some functions or some sub-collections have different names in different languages. In AOF, we have tried to stick to the OCL naming because we thought this would be most familiar to people in the modeling community. So it's actually not a first implementation of these active operations. The third iteration, there have been already 2 previous prototypes. One in Scala, which leveraged the syntax of Scala, the flexible syntax, to have an embedded DSL, basically. And the one in JavaScript, which we built to be able to use it on the web and to build interactive user interface on the web. And so this later version, AOS, has been tested much more thoroughly, much more robust and stable, and we are going to look into this today. So, as you will see, the framework is not always easy to use because the Java syntax makes it a bit cumbersome, but we have work in progress regarding using OCL as a surface query, and possibly even transformation language. So the idea is, instead of writing cumbersome Java code that uses the AOS API, in the future, you should be able to write almost regular OCL and have it use active operations in the backend of the engine, so that you will have incrementality on the bidirectional synchronization at a much lower cost than today. But of course, in this presentation, we are going to look at the vanilla active operations framework, the one that is already in the Papyrus Git repository. So it has an API that provides fine-grained synchronization control, actually more fine-grained even than what we could expect to have with a translation from OCL, because of course OCL does not know about synchronization, so when there are some synchronization specific issues to solve, it does not provide any links to address them. But of course, using the API of AOS is more difficult than using OCL. So we are going to have a quick overview of model synchronization. Then we are going to look at some examples, some demonstrations, including Christian's video on our own transformation application. So then we will look at what you can do and how you can do things with AOS before looking at what you cannot do. And actually, there are some things that you cannot do yet, but for which we have some prototype solutions which are not robust enough to be published just now. And there are some other issues which are not, for which we have no clear idea yet, but we are mentioning them so that you see what you can expect with AOS. And finally, we are going to have a little practice. So initially, I thought maybe we could have some practice altogether, but probably this is going to be too complicated. So I suggest that I will perform the coding. And Florian told me that he is recording the meeting. So in the future, you can review this video and try to follow by yourself. Of course, I can also send you after that the code by email or other means. So of course, during this presentation, feel free to interrupt me and to ask questions, or if something is not clear, or if you disagree with something I say, especially Christian, who is now an expert at this technology. So don't hesitate. So what's forward model synchronization? So basically, we typically have two models, which we are going to call MA and MB, which are related by some relation or and a transformation that implements this relation. So typically, you have this kind of settings in which MA and MB are related, and the transformation is typically unidirectional, so it can create a model B from a model A, such as MB and MA satisfy the relation that corresponds to the transformation. But there is, of course, time which appears and which makes model evolve. And so if MA evolves into MA prime, then of course the relation between MA prime and MB, which is struck out here on the view, may not hold anymore, because something that changed on one side but not on the other. So the synchronization problem in this case consists in synchronizing MB with MA prime by evolving MB into MB prime, such as the same relation holds again between the new versions MA prime and MB prime. And of course, this can be done in several ways. There is always the possibility to rerun the whole transformation, so T can be reapplied, which is what is shown on the arrow at the bottom of the slide. But of course, ideally, we would like to be able to follow this arrow here, labeled 2. So the arrow labeled 1 is the change that happened. On the arrow labeled 2 is the change, the corresponding change that we have to perform in the target module. In theory, this change will be smaller than the set of actions required to rerun the whole transformation. And so this is a performance issue, of course, but also, and probably more importantly, even in the context of editors like Papyrus, if we reapply the transformation, we will get a completely new model, a completely new set of key objects which are not connected to the graphical shapes in the editor, which will not be connected to anything in Eclipse, which means that by being able to follow the 2 arrow here, this vertical arrow, we will be able to keep the same e-objects in the same place and to keep the bindings between the semantic model and the graphical view. So these are the 2 main advantages of synchronization, of forward synchronization: performance and, of course, keeping the object identity. So, if we look at how you can express relations, even at the level of what you can express in OCL, between, for instance, 2 variables A and B. So these variables may be actually a property of e-objects or other properties, other similar properties. But here, let's look first at the abstract notation. So you can express the relationship between these 2 variables in several ways. So here we use a few functions which denote potentially complex expressions similar to what you could write in OCL. And the first one, basically, is about computing A from B using some kind of expression. And we state simply that A is equal to this complex expression of B. Then another possibility is to use a different function here called G, which explains how B is equal to this complex function. So basically, this function can be used to compute B from A. And of course, you can have more complex context. For instance, both A and B may be passed through complex expressions or functions, and then the result of these functions are made equal. So this is the third example. And finally, an even more complex case, you don't have an explicit equality relation. You just have some kind of relation between A and B. So, if you look at the first one, computing A from B is typically very easy. It's how you generally evaluate expressions in every language, OCL, Java, and so on. So similarly, for the second example, it's very easy to compute B from A because you can also just evaluate G of A using standard evaluation techniques. And actually, if you use OCL or Java, this is what you do most of the time. But it can be much more complex to compute the value of B given A in the first case, because basically you have to somehow find what kind of process F is performing and perform it in the reverse direction. It's also difficult to compute A from B from the second expression. And finally, from the third and fourth expressions, it's difficult to compute it in any direction. So in OCL, you often have constraints invariants which can be expressed like this, but then, of course, it's just a specification, and you don't have tools that can derive implementations from this specification. You can just have tools that check that the invariant is satisfied at a given time. So with active operations, we enable bidirectional evaluation of expressions structured like 1, 2, or 3. Of course, there are some cases which do not work, but it's not because the expression is structured like 3, for instance, like the third one, that we cannot work some way around it. And of course, this means that we can also compute B from A in the first case, A from B in the second case. So changes are propagated live. By live, I mean online. We do not serialize the models between each change. Changes are performed live in the editor, for instance. And they are performed at this propagation is performed at the fine-grained level, which means that basically if you add an element in a collection, the whole collection will not be recomputed. The new element will be propagated through all intermediate operations. So for those of you who know constraint programming or SMT solvers or things like that, it's a bit similar because you can write basically the expression a bit like you like, but active operations use specific algorithms, and notably they do not do search. There is no backtracking, and you are guaranteed to have a result after a small amount of time. But of course, because it cannot do search, it can only propagate changes that have no ambiguity and that do not need to be backtracked. So if we go back to our synchronization figure, basically reverse synchronization is just the opposite. You start by making a change on MB, and then you compute MA prime by applying some specific changes denoted by this arrow labeled 2 here. So when we talk about synchronization, of course, we are in a context, in a mutable context, which means that the values we consider must be able to change over time. Otherwise, there is no possible change, and so no synchronization issue. This is in contrast with OCL, which is a purely functional language in which values are immutable. With active operations, every value is potentially mutable. So to make sure that we can mutate every value, active operations introduce the concept of box, which basically wrap values whether they are immutable or mutable. So an example of an immutable value in Java is a Boolean. You have a Boolean, you cannot change its value. You can just change which Boolean is pointed at. So, because we want to be able to change the value even of Booleans or strings or integer, we have to wrap them in boxes. And of course, what makes propagation possible is that these boxes are observable. Every change made to them is notified to observers. And the active operations are basically bidirectional incremental transformations on boxes. And these boxes basically are similar to OCL collections or to singleton values, values which have multiplicity 0, 1 or 1, 1. And active operations enable live synchronization, forward and reverse. You will see a bit later that reverse has some issues. It's less easy, of course, than forward synchronization. And you can compose these operations to compute complex values, and they will still be able to propagate fine-grained changes. So to work with models, basically we just consider a model as an object graph. Edges are represented with object slots. This is how EMF works. And for us, in the context of the active operation framework, every slot is defined as a box, so every slot is mutable. So of course in EMF, every property is already mutable, unless of course it is marked as non-mutable in the meta model. But we want not only the properties to be mutable, we want every intermediate value to be mutable. So we really need this concept of box everywhere. And of course, we can connect this concept of box to EMF. This is what the EMF plugin I showed you earlier basically does. And of course, you can also connect this concept of box to other frameworks, not just EMF. You can connect it basically to Java beans, make a Java object with a getter and setter. Christian has made a connection to GMF to enable diagram synchronization, as we will see later. And you can also imagine connections to Java effects and other kinds of So the box types are very similar to the OCL connections, as I said earlier. So if we look first at the bottom part of the figure, you see that we have sets, bags, order sets, and sequences. The multiplicity is 0 star, which means basically that you can have any number from 0 to any positive value of elements. And what distinguishes each of these collection types or box types is basically whether they consider the elements as ordered, which is not the case for sets and bags, but which is the case for ordered sets and sequences, and whether they allow duplicate elements. So a set or an ordered set only allows unique elements. Each value can only appear once, whereas bags and sequences can allow multiple occurrences of a given value. And then, as I mentioned earlier, in OCL there is no equivalent to these two notions here, option and one, or at least no direct equivalent, because you can always consider that the null value is equivalent to 0, 1. But what is important here is that these boxes were singleton values, but singleton values that are mutable, so and that are observable, so that changes can be propagated. So of course, unique and ordered do not make much sense for singleton boxes, options and one, but they are true by convention. So in the API, when you ask whether one on option is unique or ordered, the framework will answer true. So let's look at a small example to explain roughly how the synchronization happens. So in this example, we have a function defined in OCL at the top left of the slide, which takes a set of integers and returns a set of integers by applying the 2 times e function on every element, which means that basically it will return a set in which every element will be the double of the corresponding element in the source set. In AOF, you can write this as shown on the bottom left of the slide. So instead of having sets, you have iSet. Then you perform a collect. And here we use the Java 8 syntax because it's much less verbose than using inline classes, but we will show in later examples that it can work also with Java 7, of course. So how does this work? Well, when you add an element in the source set, of course, we can compute the double of that element, and we can add it in the target. If you remove an element from the source, we just remove its double from the target as well. And if you replace an element, we replace the double of the old value by the double of the new value. So this is basically what happens, but you don't have to care about the algorithm details because they are abstracted out by this collect function. So now if we want to have bidirectionality, we have to specify how we want reverse propagation to happen. So in this case, in addition to the forward collector, the function that is used in the collect in the forward direction, we specify a reverse collector, which specifies how to compute a source value from a target value, the value of an element of a source set from the value of an element in the target set. So here, it's easy to see that these two functions are the inverse of each other. There is a bijection. If it was not on double but on integer, of course, there would be a bijection, so there could be some issues. Also, you see that here we have to specify both the forward and reverse collector, but in such a simple case, for instance, it may be a bit overkill to require the user to always specify both. So we can imagine that if we started from a more high-level syntax similar or like OCL, we would be able to derive this automatically, but not in every case. So how does the reverse propagation work? Well, if you add an element in the target, we apply the reverse collector and we half it by applying the E over 2 function, and then we remove the result from the source. And of course, I mean, if you want to remove, you remove it from the source, and if you want to replace, the same principle. Of course, we have to avoid infinite cycle because if you perform a change in the target, it performs a change in the source. And that new change must not be propagated forward because it would then be again propagated backward and so on. So to avoid this, we simply, in the framework, ignore the backward event that comes, I mean, the event that comes from the propagation itself. So if propagation induces some events, these events are not propagated any further in the backward direction. But of course, if there are other operations in the direction of propagation, they will be forwarded along the data flow. So AOF has many other operations. As I said, they are based on their names are based on OCL operation names. So there is collect that we have seen. There is a select, which is used to filter a collection according to a predicate. You can also ask for the size of the box or collection. You can also check if it's empty or not. You can perform union of boxes. You can convert between the different kinds of boxes. And there are also collection operations which are specific to AOF. And we will see why. For instance, collect to and collected from are similar to collect, except that they keep a traceability information, which means that if you use it in a transformation context, you can retrieve the same computed value that was computed in a prior execution and avoid computing new values all the time. So this is very similar to traceability as it is implemented in transformation language. Then you have the bind operation, which is used to synchronize two boxes. So two boxes that are bound together will propagate changes from one to the other and vice versa. Switch collect is a specific version of collect, which basically includes a select in it, but it's not just simple selection. It's more like applying a different function depending on a set of predicates. And this is especially useful when basically you want to implement rule matching, for instance, in a transformation, but it can also be useful in typical OCL expressions if you have an if-then-else inside of a collect, for instance. If the condition depends on a mutable value, you need to handle it specially, and this is what switch collect is about. And then you have, of course, conversion to one option, which are not standard OCL because OCL does not have this one option of types. Of course, once we have a way to compile from OCL to active operations, the code generator will make use of these operations, but this should be, we hope, and we are confident that in many cases, this can be made transparent for the user. So these new operations, we will have a quick look at them today, but ultimately, hopefully, they will not be available to the user because the user will not need to directly interact with them. So most operations are at least incremental, which means that they can forward changes from the source to the target. And if provided with enough information, they are also bidirectional, like for instance, the collect that we have seen previously, which becomes bidirectional if you provide the backward or the reverse collector. So we are now going to look at a couple of examples to see a bit more precisely how propagation works, and then we are going to look at some demos. So let's consider S, a mutable value, basically an ordered set in this case, which contains three values, three integer values, 1, 2, and 3. And we want to compute this expression from this ordered set. So we will first collect the result of adding 2 to every element. So from 1 to 3, we go to 3, 4, 5. And then we will select those elements which have a value greater than 4. So we end up with a single value, which is 5. So if now a change happens in the source, X. So you see I'm switching between slides. I don't know if you can see the animation. If we replace 2 by a 4, then of course it makes the intermediate value on result obsolete, which is why they are grayed out here. So what happens next is propagation, step-by-step propagation. So the change is propagated to the result of the collect. So 2 is 4, sorry, which was 2 plus 2, is replaced by 6, which is 4 plus 2. And then the next step is propagation to the select, and the 6 is added before the 5. So if now we start from the same setting, but we want to perform reverse propagation. So let's add a 6 in the order set, in the target order set. And of course, the intermediate and source values are now obsolete, which is why they are again grayed out. The change is propagated back to the result of the collect, and then it is propagated back to the initial value. So as you can see, there are several ways the 6 could happen to be here, but because we have seen just in the slide before that it could be the result of changing 4 into 6. So we could imagine that 4 could have moved on changing value. So there are several possible ways to propagate a change backward, and what active operations do is generally the most simple propagation, which is generally, of course, the expected one. If you want other kinds of propagation, it's of course possible, but then you have to implement your specific operation yourself, within the framework. This is possible, and we have done so, for instance, when we have created some new operations, but it's something that's more complicated than simply using the framework, obviously. So I'm now going to show you a first demo, and then we're going to have a look at Christian Damo's videos, which are very nice because they have
Hi. Sorry, can we make some questions here? Is it possible to add a question or ask a question for this example? It's
yes, don't hesitate to interrupt me and to ask questions.
Okay, the big question here is, what happens if I would add the 6 to the target order set before 5? So in this sense,
because it would be an insertion, basically, what would happen is that you will also insert here a 6 between the 4 and 5. So basically, what active operations do, they keep the kind of change. So if the change is an addition, they propagate an addition of elements. If the change was a move, they would propagate a move change. As I said, there are, of course, several possible ways to propagate, and active operations by default will propagate using the most obvious way, but because it's not always what you want, there is always the possibility of defining your own custom operation with a specific semantic. Of course, it's also possible to imagine, but we have not worked on this yet, to have parameterizable operations which could have semantics, generic semantics, which would be configurable by some parameter at instantiation time, at the time of creation of the operation.
Thank you very much. Okay, thanks.
Okay, so again, I repeat, do not hesitate to interrupt me, because we are here to explain things, so if it's not clear, we can take the time to explain. So I'm going to switch to Eclipse. Okay, so here I am in Eclipse, and you can see that I have several plugins here, including the AOF plugin. You also have the test plugins, some documentation, some Java documentation which was generated from the Java code in the core and EMF plugins. We have not committed this to Papyrus because it can be recomputed from the source, but it would be interesting to host it somewhere on the website. And then we also have this facade project and UML-RT project. And basically what this is about is the transformation between a UML profile and a DSL metamodule. So the idea is, when you have a UML profile, you can also you could also build a metamodule corresponding to it. And if at some point you want to work with either one of them, it would be nice to have live synchronization. And so this is what this example is about. So in this example, we are going to see several things. So this example is not based on the version of AOF which is in Eclipse. It's a slightly modified version, but the practice we are going to do later will be based on the version in Eclipse. And so the modifications basically that are in this version, I think we are not going to see them in the demo. It's only by looking at the code and trying to understand how it works that we can see what they do, but we are going to discuss them later in the presentation. So I'm going to start Eclipse, I mean a runtime Eclipse, because this demonstration is about showing how you can interact with modules that are synchronized. So of course, while the Eclipse is loading, I can comment on the other test plugin here. So we are going to see a bit later in this webinar that we can test, or that we should test active operations on synchronization tools built on active operation. And I'm going to explain later how we can do that. So for this demonstration, we are going to simply use the Eclipse reflective editor. But then in the next two demos, which are based on Christian's work, you will see much nicer graphical editor-based demonstrations. So here I have just loaded a sample UML module, and it's a bit slow. I don't know exactly why, but it's loading some dependencies. So the synchronization has not started yet. So this is just plain UML startup time. Okay, so you see it has loaded every dependency that is used directly or indirectly. So now what I'm going to do is to start the facade 2, and within the same resource set here for demonstration purposes, it has created, sorry, this is the meta module, it has created a target module. So the source module is at the top, and the target module is at the bottom. And so you can see that for a class with a stereotype capsule, we have an instance of the meta module class capsule. And for a class without the stereotype capsule, we have a passive class which is created in the target module. So we can have a look at the inner parts of these classes. So here you have a capsule part which is transformed into a capsule part instance. In the passive class, you have an operation, and there is a state machine that is put in a passive class is not transformed, but the state machine that's in the part class here is transformed, and you can we can open all these things. Okay. So what's interesting is to see what happens when we change one of these modules. So we are going to start by changing the source module. So for instance, if I move this passive class, you see that it has moved also in the target module. Now I can also try to apply the capsule stereotype to it, and you can see that now it is a capsule. And we can also try to remove the stereotype. Sorry, I chose the wrong action. And then it's back to being a passive class. So we can also move things around, as I showed you, add some elements. For instance, let's add a capsule to the target. And there is a corresponding capsule stereotype class which was created here. We can change its name. We just have to find the name property here. Let's call it test. And you can see that the name was propagated here also. Let's change it to uppercase test. And you can see that this time it was reverse propagated. So what you see here basically is a UML module, a profile UML module and a module being kept in sync, such that if, for instance, the UML module is loaded in Papyrus, you can play, you can use the editor to play with the layout or with the semantics. And on the other side, if you have Java code that leverages the specific API generated for the meta module, you can write simpler code because you don't have to deal with the stereotypes anymore since you have a DSL meta module.
Hi, can I interrupt quickly? The question of stereotypes is very interesting to me because applying a stereotype doesn't actually make a modification that's observable on the object that's applied to. So what are you doing in the AOF to detect changes like that?
So actually, this is a very good question. This was one of the issues that we encountered, but actually it was already solved by someone else. So I can show you how we do it. If I remember correctly, it's in the generic facade project. So basically, this facade project contains everything that's generic to any transformation between any pair of profile and metamodel. On the UML of this facade is just using this generic stuff. So if we go here, basically we use this Papyrus listener, which we create using a Papyrus stereotype listener, which is from the Papyrus UML tools plugin. So basically what this class does, probably we can open it, but well, no, we cannot because I don't have the source, but basically this is something that we reuse actually, and what this class does is it listens for changes on the base underscore class or base whatever property of model elements that correspond to profile, to stereotype, to applied stereotypes, and it converts the change on that element into a change on the base element. So this is an illustration showing that even if we don't have direct support for notifications on some aspects of the UML metamodel, notably, this can usually be engineered around. So in this case, we did not leverage AOF, we simply reused an existing mechanism.
Right, injecting custom notifications that AOF into cloud. Okay.
That's how it works. But of course, there are several possible ways that we could have overcome this issue. But reusing something that's already developed and proven sounded like the simplest and safer way to proceed. And actually, if you think about it, there are other things in UML that do not notify of changes, notably some derived features, actually a significant amount of derived features. And we have already discussed this issue with Florian, and he has suggested that since inquiry has some tool support for this, of course, instead of redoing the work, we could simply leverage it. So basically, whenever we can find something that detects the change, and we can actually generate synthetic events or connect one of our observers to the event source, we can overcome the issue. For these derived features, an alternative, of course, would be to rewrite them when it's possible using active operations. But as I said, the objective is not necessarily to do everything using active operations, but to use them when they are appropriate and to reuse mechanisms that work already for other issues.
Okay, that makes sense. Thanks.
Is there any other question before we switch to the next demo? So I'm not going into the code now, of course, unless there is a specific question like about stereotypes. But if you want to see something, don't hesitate to ask. We have many more things to do, but if we have some time left at the end, of course, we can also go back to have a look at how the facade works, because basically it leverages active operations, but it's a bit more than active operations. For instance, regarding stereotypes, it raises this mechanism to encapsulate it so that you don't need to care about it when you write the transformation, but it's not the only thing that it does. So I'm going to mention some of the things it does later in the presentation. And if you want, we can go back to see how it can be used or how it is implemented. So I'm going back to the slide. So let's start with the first video. So it's on YouTube, so I'm not sure it's going to be very fluid through the webinar. So if that's the case, I can stop it if it's an issue, but you can also have a look at it directly with YouTube. What you see here, maybe Christian can comment it?
Yeah. So basically, what I've got so far in my diagram synchronization prototype is using. It's a very simple use case of the active operations to, on the one hand, synchronize the layout and appearance of views in different diagrams that here in this example of a class diagram is two different diagrams visualizing content from the same package. So this is basically the simplest sort of synchronization scenario that we're looking at. A particular concern for my use cases is that generally the synchronization we want to do is in one direction only, in the forward direction. And in the diagram here on the right side that is synchronized from another one, we do want to be able to customize its presentation in some way, add elements that aren't visualized in the source diagram, rearrange the layout to accommodate those kinds of differences. So it's a selective synchronization, and as the user tweaks the presentation of the synchronized diagram, there are synchronizations that we want to snip and just discontinue. Then so it's on the one hand it's not bidirectional, and on the second and also it's more fluid and selective of which subset of a model or a diagram we want to synchronize at any time. So that the set of things that are synchronized evolves, changes in various ways. The other more complex use case that I think we're getting into now is where we're synchronizing not just visualization and diagram, but also elements in the semantic model. So in this case, a state machine that redefines another state machine, we synchronize elements of the redefined state machine into the one that redefines it. But the redefining state machine can add additional elements, states, transitions, and can rewrite some of the states and transitions that it that it redefines from the parent state machine. So that's again a case where we have this selectivity of what the user wants the system to synchronize from one state machine to the other, and that changes over time too. So again, it's not a bidirectional synchronization scenario, but we do need the tool to detect when the user's making changes on the target side of this forward synchronization that needs to break that forward synchronization chain for those elements. So I think the demo video should be getting to an example of that shortly. So here, propagating changes from the parent state machine to the other when we redirect the transition. Undo and redo needs to work, of course, in a tool like this in the way that the user expects. So as the tool establishes new synchronization relationships or breaks these synchronization relationships, that those sort of meta changes need to be undoable, redoable within the tool. I guess I'm talking at some length here about something. It's a bit bizarre watching my own video here in closed captions.
Yeah.
But
the
my memory of it is fading too. Yeah, I do tend to mumble also sometimes in these videos. But the automatic CC can be a challenge.
We can stop this video and switch to the next. But before that, I wanted to show the code. So basically, the code corresponds to this video, if I'm not mistaken, in this AOS sync branch of yours. And so you can see here along the regular AOS plugins, you have the TMS connection on the examples on the synchronization framework.
Yeah. So the synchronization framework. Sorry.
Yes. Go on.
Yeah. So what that synchronization framework, the main objective of that is to add some bookkeeping type layer to help keep track of which operations we've instantiated on our model to perform our synchronization, so that when we need to, we can deactivate them, we can remove them again when we need to break the synchronization relationship between diagrams in various discrete places, and a bit of an EMF model that keeps track of some of that helps with implementing the undo and redo of the synchronization operations in the UI. So it's basically this a kind of organizational layer on top of that to help us to manage the active operations that we've instantiated on our models. And in these particular use cases that I've been looking at so far, it's basically just using maybe one example of a whole bunch of collect operations and the bind operation to synchronize these intermediate collect results between the diagrams. So it doesn't really go very deep into what the ALS can express in terms of transformations. Because as you can see in the demo example, that it's really just binding values of notation and the semantics. It's not doing anything more complex than that at this point.
Okay, so maybe we can have a look at your second video, which, if I'm not mistaken, basically corresponds to this new branch in which you have performed some improvements. So I'm going back to the presentation. Oh, by the way, maybe I should mention it now for those of you who are interested. Christian is keeping a trace of all his work on this project on Bugzilla, which is how I managed to follow his quick pace. I noticed that he made a commit less than 10 hours ago. And so we got, sorry?
Oh, just saying yes, yeah.
Yeah, okay. So let's have a look at the video that maybe you can again comment.
So my work this week, and was Eclipse gone last week? Yeah. So my work this week has been focusing on persisting somehow these exceptions in the synchronization of our diagrams. So what I mentioned before, where according to what the user customizes of the layout or content of a diagram that is synchronized from some other diagram, up to this point, my prototype hadn't accounted for persisting any knowledge about what the user had customized. So when you reopen the editor again in another session, it would detect that it's got these diagrams to synchronize, would fully synchronize them, and then they end up looking exactly the same again. So this week I worked on styles and other annotations that would be persisted in the diagrams and in the models to basically record a trace of what had the user done in a synchronized diagram to make it different from the source, so that we won't attempt to resynchronize those elements the next time. So at this point in the video, we're just setting up this very simple, again, in this fake UMLRT-like language. These on the right, we have a state machine that's redefining the state machine on the left that it's synchronized from. So just setting up a little bit of a scenario here. And so here is just having a look at how the synchronization establishes the correspondence of elements in the two state machines using UML's redefinition relationship. So on the right-hand side, states and transitions redefine, and there's a specific UML association for that in the UML meta model. They redefine corresponding elements from the parent state machine. So here's an example where now I'm about to go on the right-hand side and change the layout of that state in the redefining state machine. So there I've done something to break the synchronization. And so that, although those states still correspond and the semantics of them in the UML model are still synchronized, now their notation of the diagram isn't anymore. And presumably the reason why the user did that was to make a specific layout in the redefining state machine, because there will be some other content added in there that isn't in the parent state machine. And so here I'm just demonstrating how, as we saw in your UML RT facade demo, how changes in the semantic model are propagated from left to right, but then when I make a customization in the on the right-hand side, it isn't propagated backwards because that's not how my use case works. And then that breaks synchronization of that particular attribute going forward. So here, this was the state of the art before this week, where now we reopen the diagram, and because the diagram doesn't remember that I made any kind of customizations to the synchronized diagram, it just, when it woke up, it just resynchronized everything again to make these two match exactly. A little bit of a joke in the middle, and then this is the new branch. that has this new capability of remembering what does not need to be synchronized from the left side to the right side. So again, we're starting from scratch with a scenario. We see how these diagrams are synchronized left to right. Now I make some kind of change on the right-hand side. That state 2 is no longer synchronized. As you can see there. But other elements of the diagram still are synchronized. Here I'm changing this transition to be sourced on a different state in the redefining state machine, although it doesn't change the fact that that transition does redefine the one on the left-hand side. So now I close the diagram, or the editor, I open it up again, and now because I've persisted information about the notation and semantics that are not synchronized, there are exceptions to the synchronization pattern. The diagram doesn't wipe away all the work that I just did when I open it again. So besides the actual transformations that I do, that I set up with AOF to accomplish synchronization, there's a lot else to manage in these use cases of which specific subsets of models and notation that we want to synchronize and that we don't.
So basically, the purpose of showing you these demos was to give you an idea of the kinds of things that you can achieve with AOF. But of course, we have not seen everything that's possible with AOF. We have not seen all the details of how these things work, but at least it gives you a rough idea. So now we're going to have a look at what you can do with AOF and how you can do it and how you should not do it also to avoid common traps. So basically, what's the status of AOF? Well, it already provides, as we said earlier, most of the useful select, collect, and some variants operations with synchronization algorithms that we have extensively tested. And there are already two complex synchronization frameworks which are built on it. One, which is the facade application, which I demonstrated earlier, and the one developed by Christian with the application to diagram synchronization. And as you have noticed, there are some differences because in our case we tried to have as much bidirectional synchronization as possible, whereas in a Christian case, forward synchronization is enough, and actually he even wants to be able to stop synchronization at some point to be able to perform some changes in the target that will not be propagated backward and that will not be overridden by further changes in the source. So this shows that AOF can be adapted to different application cases. And notably, there is a built-in feature, as Christian mentioned, that he needed to disable the bindings at some point. And there is a built-in feature in AOF for this, which is used with one purpose in the facade application, but with another purpose in Christian's work. So our objective for the future is to have as much generic facilities in AOF as possible, so that different application cases can leverage them in possibly different ways. So let's have a first look at one of the most trivial things you could do, which is binding object properties. So we are going to consider named elements, which have a name property of type string. There is some noise in the phone. Okay, it's intermittent. So in this example, you can see that this method will bind the names of two objects. So it starts by creating an instance of the AOS factory. So of course, in actual code, this should probably be in object property, which does not need to be repeated in every method. And what the first part of the next statement does is create a property box for the name property of the T object, and then bind it to the name property box for object S. So as you can see, every property access is wrapped in a box on AOS factory. Does this for get set properties like you have in Java Bean. And the bind operation is used to keep both of these boxes synchronized. So every time there is a change in one of them, it is propagated to the other one. So the thing to remember about the bind operation is that it initially performs a copy from right to left, or as a method from its argument, from its argument box to its source box. So here it will copy initially from S to T. So which means that basically when you have transformation, typically this will be the forward direction. Of course, in some contexts, it may not be appropriate to bind in this direction, and then you can, of course, bind in the other direction. This is the kind of thing that frameworks like Facade can do on top of AOS. Basically decide whether to apply the binding in one direction or the other initially, and after that, anyway, it will keep synchronization going in both directions. Of course, at some point, you may also want to disable the binding, so this is also something that's possible. That's not demonstrated in the code here, but it's possible because the bind operation returns a binding object which can be used to disable or re-enable the binding. So if you use EMF, basically what changes is, of course, you have the E object instead of plain Java object, and you use the EMF factory to create your property box, because instead of simply looking for get set properties, it will look for structural features from ECOR, and then it can, of course, leverage the observable capability of EMF. Because what I did not mention here in the previous slide is that for plain Java objects, of course, the get set properties, if you want them to be observable, they have to return some kind of box, of course. And for EMF, we don't have this requirement because otherwise it would mean changing EMF to return boxes. But rather what we do is we connect boxes to EMF properties with the EMF platform plugin. And this is something similar that Christian has done for GMF, and that I mentioned earlier could be done for JavaFX or other platforms which provide observable properties. Actually, in the JavaScript version of active operations, we use the observable DOM events to perform the same kind of property bindings that you see here on EMF. So even though we are using EMF factory, we can still use property names on the tool will look up the actual structural features for you. Of course, if you use generated EMF, then you can have more static typing, and you can use the actual structural features using the package instance API from EMF. So here demonstrated with UML. So although objects are statically typed, and properties are not just strings as before, but are actual structural features, this does not completely type statically, because the EMF E-attributes, or E-structural features in general, are not generic. So they don't, I mean, the type here, E-attribute, does not inform the compiler about the type of the property. So here, if we add an E-attribute with a type parameter string, for instance, we could leverage this information to make sure that we are not binding two boxes of incompatible types. But because we don't have this information here, we cannot type this statically. We will see later how you can overcome this, basically by defining your own wrapper around E-structural features. And this is something that's interesting because it helps make your code statically typed and so statically checked, at least to some extent. So in this slide deck, we are going to use this simpler pseudo-pass notation. Yes?
Could you go back 2 slides to the plain old Java object version?
Yes?
Yeah, this one. If these are S and T are plain old Java objects, then how do you ever get a notification if the name attribute changes?
Yeah, so you're right. So what I mentioned is that this, of course, can only work if the getSet properties can only be observable if they return proxies. So, of course, when I say it's plain old Java object, it's a bit cheating because actually plain old Java objects that are meant to use with the AOF API. But if it's EMF, then of course we have notifications built in, and similarly for Java effects.
Thank you.
Okay. So I was saying that in this slide, we are going to use this simpler notation in several examples, because basically, as you have seen in the previous slide, the code can really get verbose quickly. So basically, when it's non-ambiguous that we do mean property access wrapped by a box, we simply use the dot notation. But this T.9 here really means its factory that create property box and so on. And this operator corresponds to the bind method. So of course, this is just a pseudocode to help save some space in this slide and make things hopefully clearer. But ideally, once we have the translation from OCL to AOF, the idea is that you would be able to write something very close to this, probably with just a standard equal operator instead of this funny one here. But of course, the result would be that you have a nice syntax, but actual EMF AOF operations still. So of course, this conciseness that we see on this slide shows that such specific syntax is needed if we want end users, or at least regular Papyrus users, for instance, to try this kind of thing. But for now, as I mentioned earlier, we are still at the framework stage. So this is the kind of thing that we are going to use. But of course, we are stuck with this Java API, but we can still make it simpler. For instance, here we have defined a specific bind method, which takes both the source object and the name of its property, as well as the target object and the name of the target property, and performs all the boxing and binding, so that what we have here is much simpler to write and to read. Of course, the problem is that if you want more complex bindings, as we're going to see later with filtering or mapping or and so on, this is going to be a bit more difficult. But for instance, in the facade example, most bindings can leverage this kind of method. Of course, we have several variants which enable filtering and so on. But by leveraging this kind of method, there is also one additional property, which is that the bind method can actually decide, based on some other contextual information, whether to bind S to T or T to S. And this is, for instance, what we use in facade. When you create an element in the target module, or when you add an element to the target module, it of course binds the properties from target to source and not from source to target, so that the target information is kept and copied to the newly created source element. So the next step is to look at how we can collect values. So in this example, we still use the named element meta class, except that this time we decide to prepend an E, a capital E, to every string, because this seems to be something that EMF likes. So as you can see in Java 7, you have to have this inline class and method definition. But of course, with Java 8, you can have a much simpler syntax. And actually, AOF is compatible with Java 7 and can be compiled on Java 7 because it has to be compatible with Papyrus, which is Java 7. But if you want to use it with Java 8, you can leverage the lambda, of course. And if we use yes?
Sorry. Yeah, so for the Neon release, Papyrus is up to Java 8 now. So if that's the reason why you're making API decisions in AOF, then that reason is gone.
Yeah. So basically, we originally with Florian, we decided to go for Java 7 because we aimed at a Mars release, and actually the code was published on Eclipse on Gerrit at least before the Mars release. But of course, now probably we could go to Java 8. In any case, what's important, I think, is that user code can use Java 8 syntax with Java 7 AOF. So of course, because you can do this, it's less of an issue. Yeah. Okay. Thanks. So again, we have this pseudocode notation in which we tip the Java 8 notation because it's concise enough. So now that we understand what is behind this pseudocode, most of the examples I will give later will just use this and not give the corresponding Java version, except when it really helps to disambiguate problems. And now I have a question for you. Do you think this binding works both ways in this example? Let's see if you have followed closely.
Well, I would say it doesn't.
Yeah. It doesn't because the framework is given a closure, the lambda expression. So basically, as we know in Java, it's just an object with an apply method. And it cannot reverse it. Actually, it does not get the syntax tree. It really gets just a way to call this. So the solution is to give a reverse collector, as we have seen in the previous example. And here we have one in which basically we have the same collect with the same function here, but we have an additional function which goes from target to source. And basically what it does is remove the initial letter. So of course, if we had the generator or compiler from a specific syntax, which we aim at with OCL, then we can automatically reverse some collectors. But sometimes collectors are not reversible because they are just not built in a way that you can have a meaningful reverse computation. Or sometimes it may be reversible in several ways. And in that case, we suppose that the best way to address this at an OCL-like syntax level would be to let the user annotate some kinds of comments or whatever, the code to specify which kind of reverse semantics they want. And actually, if you think about it, this reverse collector is a partial function because it doesn't work for empty strings. So which means that if you pass it, if you add an empty string in the target, in the result of the collect, then there will be a problem. And actually, it can also reverse strings that are not prefixed by key, but that are prefixed by something else. So probably this reverse collector is not always what you will want to use. But that's just an example, of course. But that illustrates what we mentioned earlier, that you have to decide which reverse collector to want in which context. And basically, it's up to you to make sure that your forward and reverse collectors are compatible. Ideally, of course, if the function is bijective, then the functions should be the inverse of each other. But in other cases, it can be a bit more tricky to decide what you want to do. So if now we want to look at selecting values, so we are not just collecting, but we are trying to filter collections. So consider, for instance, a person which was email addresses. So these email addresses from a collection of strings. So it will be a box of strings for iOS. And what we do is use the select operation, and we give it a predicate, which, for instance, here selects only email addresses which end in .fr. Of course, this can work in the reverse way, but only partially, because you should only add in the target email addresses that satisfy the predicate. Otherwise, you will get an exception. But it becomes more complicated when you want to select objects, not just values. So we are going to look at a more complex setting here. So we have a person who has email addresses, and each of these email addresses has a Boolean property called isPublic. So naively, we may try to write the select in the same way as before by using isPublic. So we suppose that we are using generated EMF here and that we can directly call the method to get access to the value. But the problem is that select takes a Boolean as the result of this predicate, and isPublic actually returns a Boolean, and in Java, Boolean objects are immutable. So they are not boxes. Remember, we said at the beginning that we need every value to be boxed to make sure that every value can be mutated. So in this case, it is not possible to change the value. So the value, of course, in the module will change, but the active operation, the select, will not get notified of this change. We cannot know from the information it is given when this has changed. So a small warning here, if you write this, and if you test it without testing propagation, of course, it will have the proper behavior. But once you start modifying the source of the target, the propagation will fail, and it will not fail with an exception or something dramatic. Rather, it will just fail to propagate. So it's very useful to test these kind of things to make sure that you got it right. So another solution, which, well, actually this one is not a solution, but a solution is, of course, to use this create property box method that we have seen earlier, because it will return a box of Boolean. But then, of course, we need to use a different version of select, because select, as I said earlier, expects its predicate to return a Boolean. So here we need a mutable version of select that expects its predicate to return a box of Boolean. The problem, of course, is that once we have this box, we can, of course, give it to select table, but can we do anything else? For instance, suppose we want to negate it or to combine it with Boolean operators. Well, because it's a box, it does not have these capabilities. And of course, if you unbox it, then it loses the observability property. So we have to find some way to do it. And so this is why in AOS there is this mutable predicate class, which represents functions that returns boxed Boolean, and that offers to combine them using standard Boolean operators, but also provide few predefined predicate builders. So in this case, we use the property equals predicate builder, which will basically return a predicate, a function that takes an argument and returns the boxed Boolean, which checks, which denotes whether the isPublic property is equal to true or not. And then, of course, using this kind of mutable predicates, we can combine these property builders. For instance, here we can check that isPublic is true and isObsolete is not equal to true. And this will correctly propagate predicate information into the select table, which will therefore correctly propagate chances. Of course, here, because we use the property equals, instead of using not, we could simply have done isObsolete false instead of true here. But of course, to show you this possibility, I prefer to do it that way. So here is another selection example, which is similar to the one we had earlier, except that this time, instead of having just a string, we have a string value which is accessed via reference, which means that the value has to be a property box. So here we are using this pseudocode syntax, which means that here there is a property box creation. And then we have to collect on this value, and we can use the standard ends with method. But we have to make sure that we handle the null case, because first, of course, the value may be null in some context, but more importantly, because actually AOF uses collectors or selectors. Actually, yes, because in this way it can get the default result value, and thus it can get the properties, unique, ordered, and so on, of the result box. Or it can use it to correctly type the result box. So here you see that we use a collect inside the select mutable, and this is how we can apply the ends with operation to the box value. So now that we have seen some of the things we can do with AOF, we are going to look at some of the things we cannot do with it. And of course, I will tell you when some of these things are actually not possible because we do not have an idea of how to solve it yet, or just because we have not had time to mature these ideas yet. So, as you have seen, AOF has no notion of transformation rule, which means that matching, it does not really perform matching by itself. It can just do selection and things like that. The guards that you find typically in transformation rules, also, you cannot directly express them, although you can use some select, but it's less powerful than guards. Of course, if you want to enable bidirectional synchronization, which is not always the case, as Christian has demonstrated, but when you want it, you want to be able to handle both forward and backward element creation, which basically requires more manually written code. And bindings are not automatically enabled or disabled. AOF provides you with the capability to disable and re-enable bindings, but it does not know by itself when to do it. An example in a transformation like the facade example of a time when you want to disable a binding is when you have this, maybe I can go back to Eclipse, when you have this passive class to which I applied the capsule stereotype. Instead of having a passive class in the target module, we had a capsule, which means that we had to create a new module element, because in EMF you cannot change the type of any object. You have to create a new object, which is an instance of the new meta class. Which means that the same source class name, for instance, would be bound to both the passive class and the capsule, even though the passive class would not be in the module anymore. So I can do it again to remind you what I'm talking exactly about. So you see, if I apply the capsule stereotype, the passive class here, look at it while I press OK, it transforms into a capsule. And actually, there is still a passive class, but it's not part of the module anymore, but it's kept by the bookkeeping traceability code. It's kept in memory. So now we have the same element here bound to two target elements, and of course this can cause some problems. So what Facade does is that it disables binding when an element is not matched by a rule anymore, so that if it's matched by another rule as a side effect of not being matched by the first one, there will be no binding conflict. So this is the kind of things that you need, but that AOF does not provide to you. However, because it does not provide to you this kind of semantics, it's not tied to a specific transformation approach. You have understood from my presentation on my demonstration on the Christian's demonstration that there are several possible semantics that we want to give to synchronization solutions. So actually, AOF is more like a synchronization enabler that does the hard propagation work by using these specific algorithms. And so AOF opens many new opportunities that we can leverage, but of course, for each of these opportunities, there may be some specific values that for which you may want specific solutions. So this is why typically you will reuse or build or customize a framework on top of it, like Facade, which I have just shown again, and like Christian's, which you have seen in the YouTube videos. So another thing that AOF struggles with, like many synchronization approaches, is structural mismatch. So in this example, which is actually an excerpt from the UML scenario, you can see that an operation in the source on the left has parameters, several parameters, and each of these parameters has a kind and a type. And the kind is either in, out, or return. So actually, this is an excerpt from the UML metamodel. But in the target, an operation has parameters and a return type, so which is closer to what you have, for instance, in C or Java, in which you have only one return parameter on its return type, and it's specified separately from the list of parameters. And so you can write the expression which is at the bottom of the slide here. So of course this is in pseudocode, so there is all this box creation that is abstracted away for simplicity. So you get to bind the return type of the target to the source parameters that satisfy this predicate, so the direction has to be returned. And of course here I used pseudocode, but of course you would need to use some kind of mutable predicate property equals direction return, similar to what we have done earlier. Then you convert it into an option to convert it into basically a singleton, and you want to get the type. And here there is one thing that I have not mentioned earlier, which is this collect mutable, which is basically the equivalent of select mutable for select, but select mutable does the work for collect. If you collect mutable value, of course, you have the same problem. If you want to be notified of changes, you have to listen not only to the source box, but also to the property box here to the type of the parameter. So the problem here is that if you add a type, it will get propagated to the select, but for it to work correctly, it should instantiate a new parameter. And in the version of AOF that is on Eclipse right now, it will not be able to do that. However, we have made some prototyping to overcome this issue, and we have realized that in some cases, and in this case, the case, that it can be applied, because we have only one of the two path elements which is multi-valued, and the other one is single-valued, then it means that if we add the target type here, basically there is just one way to make this work, is by adding a parameter which kind is returned. But for this to work, of course, you need to specify the code that will create the parameter. So we have made some prototyping around this, but this is the kind of thing that you cannot do directly with the AOF version, which is on Eclipse right now. So this shows also that depending on the use case in which you want to use AOF, you may get some of these difficulties. So what's important is that we identify them so that we know which problem other users may encounter. And once we have identified them, we can focus on finding some solution like we have done for this one. So another thing that is not in AOF is full support for OCL, especially for its collection library. So right now it's not so much of an issue because, as I mentioned earlier, the most select and collect. But if we want to be able to translate from OCL, of course, we need to have broader support for its API, its library. So, for instance, all these operations could index of, includes all, excludes all, maximum and minimum, the sum, which basically is a fold with a plus operator, the product, which is a Cartesian product, the sequence order manipulation or subsequence or reverse and subsequent operations. For these, we have some clear ideas on how to implement them. Actually, some of them are already implemented in the previous active operations prototypes in Scala and JavaScript that I mentioned earlier, but they have not been extensively tested, at least not as much as those that are in AOF right now. So they are not considered mature enough. So they were left out of the version that was published. So the rationale was that it's better to publish only operations that we have extensively tested and leave the rest for when we have time to really focus on them, so that we don't produce broken behavior on which some users may spend some time debugging or may even rely on. And actually, we have basically implemented those that we needed for the facade case. And as Christian mentioned earlier, he mostly uses select and collect, which are really the most useful ones. So if we continue to look at the social collection library, there are some set-specific operations which may be slightly more difficult, but should probably be possible to add, like set intersection, set difference, and set symmetric difference. Then, of course, we have iterators. So the iterators in OCL basically are the operations that take a closure as arguments, like collect and select. And there are actually some of them that can be done by equivalence, as it's shown for exist. If you have an exist iterator, you can often replace it with a select not empty, because basically if there is an element that satisfies the predicate, you will find it by selecting, and you will check if it's there or not by asking if the box is empty or not. Then there is also the for all iterator, is unique, one, and sorted by. So all of these should be doable. Sorted by may be slightly more difficult, but we have some idea. Basically, we would have to play with indexes of elements, because we have to make sure that we keep the relationship between the source and target indexing. One additional thing to note is that exists and for all can support multiple iterators in OCL. And right now, we don't have iterators with multiple, operations with multiple iterators. But basically, it seems like it could be just a matter of applying a kind of deep operation, which strangely has never been added to OCL, but which is very useful in functional languages, which is even available in languages like Python. So, for which actually we have an implementation. So this probably could be on that. And then there are some more complex OCL operations, which are nonetheless useful, but which probably will be more difficult to support, like closure, which enables, for instance, let's take an example, in a class diagram, to get all the supertypes of a given type by navigating the supertype relation. So from a class, you go to its immediate superclasses, and from each of its superclasses, you navigate to their immediate superclasses, and you do this recursively until you reach the root, the inheritance hierarchy. And of course, even though for this case there is no cycle, you should handle cycles so that you do not loop infinitely. Collect nested actually is similar, well, is often associated with this arbitrary flattened operation. If you want to be able to implement these three operations, basically, you need to be able to have an operation that performs deep traversals in your object graph, and the depth of this traversal is not known statically. So we have some ideas on how to achieve this, but this looks much more difficult than the previous operations that we mentioned. Then here is a quick review of some other missing functionality. For instance, if you have a select or you add an element which does not satisfy the predicate in the target, there are several possibilities. What we do now is we throw an exception to make sure that the caller is notified of the issue. But what we have thought about is that actually, in some context, it's useful to view the predicate as something bidirectional. Like, for instance, if you say that you select classes that have the capsule stereotype, in the forward direction, you just filter these elements, but in the backward direction, probably you want not only to create a class, but also to apply the stereotype to it. So right now in Facade, we handle stereotype application separately, but the idea of predicate reversal would be that basically the predicate often gives you enough information to make sure the element actually satisfies it after applying some relatively simple computation. Naturally, this is one functionality which we have prototyped on which works quite well, but of course it would be it still needs to be tested and it's not mature yet. So another functionality that could be added is to make AOF internal API active. So you remember that Christian told us that he needs to enable, or more precisely, to disable bindings depending on some condition triggered by user interaction. Actually, I've looked at his commit log, and if I understand correctly, maybe Christian can confirm, what he did is make this enablement in a box. He wrapped it in a box so that he can use AOF operations directly on it.
Yeah, so I
right,
needed, that's right, so I needed my synchronization framework to be able to observe the enablement of bindings, basically, in order to do some side effects.
So this is this is the kind of functionality that we had not thought about when we added this binding enablement feature, but which actually makes AOF even more powerful, because you can use it. You can use active operations to trigger the enablement or to observe the enablement of other operations. Then, of course, there is a big issue which is testing and debugging. So later we're going to see how we can test. If we have time, I can show you some debugging. But basically, we have built some test framework, but it's not mature yet, because it's actually to make something like this really robust is not trivial. But we have some promising prototypes. We have even played with the idea of modal fuzzing. So I don't know if all of you know what fuzzing is, but basically in the security community, fuzzing consists in sending a lot of random requests to a server, for instance, and try to make it crash. And once it has crashed, you look back at what you've done and you try to reproduce it. And once you have managed to crash the server, probably you have found a bug, and by investigating it, maybe you can exploit it. Well, here the idea is similar, said that we don't want to exploit anything. We just want to discover issues, to locate them, and to solve them. So we use this technique to discover many issues, and basically what we typically do when we have an issue discovered by the fuzzer, we immediately write a manual test to make sure that it will be tested again and again, even if the fuzzer decides next time to choose a different random path and not trigger this issue. Another relatively important issue is performance. So as you have seen in the demonstrations, AOF is quite fast on simple examples, but we still have to study scalability and of course to profile it and to optimize it. So there are many small things that we know how to optimize. For instance, right now, every box holds its values in a Java collection, even singletons, for which it's not necessary. So we know how we could save both some space on some calling and some method calling, but there are probably other issues that we have not discovered yet because we have not tried it on big enough models. Actually, maybe I'm not sure it's a matter of the size of the model or the complexity of the operations or both. But with the fuzzer, we know that in a single Java virtual machine, we've been able to test millions of changes at a time on a given model. And we managed to keep memory and time under reasonable limits. So reasonable limits means millions of tests in around 10 to 20 minutes. On a reasonable memory limit means what I have on my machine, which is 8 gigabytes of RAM, but of course not all of this was allocated to the Java virtual machine. It was more like 2 gigabytes. So another issue related to memory is to make it possible to free all memory without unloading the source and target resources. And for this, again, we have some prototype which uses Java reflection to navigate the instantiated operations in order to detach them from source and or target models. But right now, this is something that's not really mature. And actually, in the future, we should probably not rely on reflection. We should rather implement some kind of operations navigation API. But we would need to really think this through, because if we introduce such an API, we want to make it stable. So we have to make sure that it handles all the expected use cases flawlessly. And finally, we have talked about property boxes, but actually resources are not really e-objects, and their contents are not really regular e-object property. And right now, we have not tried to build observation for this. We have just relied on the fact that in both the meta models we have had to play with so far, there is always one root element, the model in UML. But this is something that does not sound too difficult, because DNF has notification support for this kind of changes. It's just that we have to implement specific algorithm for this, because we don't have the possibility to reuse the mechanism which is already implemented. Yes? Of course. I saw that you raised your hand, but I don't hear you. Someone hears me?
Yeah.
Are we alone?
No.
Okay, so I don't know why you saw this message. Oh, okay. I see that our host is actually chatting. Let me see what he says. You cannot talk for some reason. Okay. If you want, you can ask your question in the chat. So I don't know if you have a question or not. So I will continue, but if you finish typing your question, you want more details? Okay, on which issue in particular? Performance. So as I said, we have not performed systematic study on performance. We have not focused on this yet because concretely this was not the issue that we encountered. We had a lot of issues making sure our algorithms work in all cases. And basically, this required building this testing framework, including this model server. But this is one of the things we plan to perform in the future. So right now, I cannot tell you much more about this. Yes, so actually, what you suggest is to, for those who do not see the chat, is to reuse a case study that you have created on the, yes, okay. Olivier, can you keep the link? So, my assistant on bot is going to archive the link. So thank you for this. We are going to look into this. So basically what Akos is suggesting is that we reuse a case study that they have built to test performance. Therefore, we should be able to compare, to have a comparison basis. Thanks. Okay, so now I think the question is answered. So if you have, if any of you has a question but cannot talk, don't hesitate to do the same thing, to raise your hand virtually and to ask the question is in the chat. It is now open on the computer next to me. So now we are going to look at some practice. So you had a question about observable resource content as well, or maybe a remark, because probably you have solved this. Okay, so basically Akos is saying that they have a solution for this in query, of course. Thanks. So right now, what I suggest we do is that we try to look at a relatively simple transformation. It's simple because the structure of both data models is very close, which is a transformation from UML to ECOR. So the objective are to discover how you can use vanilla AOF. So I'm going to write the transformation without using facade, because basically the idea is to show you what you can do with AOF, but you will see that there is a need for more abstraction because there are some things that are going to be a bit verbose and difficult to write manually. And if we have time, we can have a look at how we could do it with facade, or alternatively, we could also have a look at how it is done for this UML or T case study. So, I have here an Eclipse in which I have imported the AOF plugin. So, I also have, I will show you now, if I find the right one. Is it this one or that one? I think it's that one. I also have another one in which I made some tests. So I'm going to do some copy-paste between the one in which I have already done some work on this one. So don't be surprised that that I keep switching from one window to the other. But what's important is what goes on in this window. And what I will do with the other window is just retrieve some code that we you will need. And I will, of course, explain when I copy-paste some code why I need that specific code. So I'm going to start with a plugin project. So I'm going to call it Eclipse Papyrus AOF examples element record. So we are going to use Java 8 so that it's going to be simpler. And so one of the things that we will need is the code to invoke the transformation once we have written it, and to test it. So this I will retrieve from my previous test, because it's not really focused on writing a transformation with AOF, it's more about testing it. So I'm just getting this. And of course, there are some errors because there are some missing classes and missing dependencies. But I'm going to review this code with you and add the dependencies as we see them. So of course, because it's for testing, we need JUnit. So we are going to add this. We also need EMF because we are writing ECOR, we are writing a transformation from EMF to ECOR. We need AOF and we need UML. So I'm going to add these dependencies now. If I add ECOR XMI, I should have all the dependencies I need. And here I need the UML resources, and I need AOF. So I will take AOF long because basically it depends on the other plugins and re-export style. So by depending on it, I get all the other plugins. And I forgot to add JUnit. So of course, as I said earlier, I will send you the project after the presentation. I will check with Florian what's the best way to send to all of you, whether it's by mail or if we can put it somewhere on Eclipsepedia or whatever. And then you can, of course, try to rewrite the transformation or to play with it later. So here, the only thing that's missing actually is the UML2 ECOR class, which we're going to write. So let's have a quick review at these two classes that we have retrieved, now that we have solved the most problems. So first, the main class is just one way to launch the transformation from the command line. The idea is by using this, we can quickly test simple stuff. And then in UML2 ECOR test, we will have more complex tests. So let's have a look at how this file is written. So we start by defining a resource path, which is basically whatever is in the module folder. So probably I should create this folder to make sure that the resources can be found. Then there is a method to initialize EMF, and we need this because we are going to run from command line, as I said earlier, and also because we are going to test JUnit also from command line, not from an Eclipse context. As we have seen in the demonstration, even though the UML-RT facade example was written in the same way, it can also work from Eclipse. The idea of being able to test it in command line is to have faster startup time, which do not require the launching of an Eclipse application or even an LTI container. So what EMF initialization does is register the eCore extension with the eCore factory and any other extension with the XMI factory. So these are some things similar to what is done in Eclipse with the OSGI on plugin.xml and so on. But here we have to do this manually because they are running command line. Then we have this method to initialize UML, which calls the initialization of EMS before. It registers the UML file extensions with the UML factory, and then it registers the UML namespace URI with the UML package instance. Then it leverages the get plugin URI method here, which basically simply gets a URI for a given plugin. And here it's the plugin of class UML resource util. And this is used to register some UML stuff like the library path map, the metamodule path map, and the profiles path map. So we may not need all of these right now, but basically with this you can load the profiles and so on. So this is very useful to have. So all of this, of course, is documented somewhere on the web, but not necessarily always in the same place. So I see Christian made a comment on the chat. Okay. Okay, so I did not know this. So basically, what Christian said on the chat is that EMF has something that can do this automatically. So here you can see how to do it manually, but of course, if you can do it automatically, it's even better. And then there is this initialization method, which is the one that will be called by JUnit before running any test from this class, which initializes UML, which gets the target metamodule, and here which disables inspection, which we are going to cover later. Basically, it disables debugging code. I see there is a new lecture. Okay, so thanks, Christian. Christian just added that there is something similar for UML as well. So EMF on UML already support initialization. So here you see that the target metamodule is a static resource, but the source and target modules are object level attributes. And the reason is that each time we run a test, we want to have a new version of the source model and the target model to make sure we really test things independently. That I mentioned earlier, of course, we want a million tests on the same model to make sure that even if there is a sequence of change that triggers a problem and not just an individual change, then we get to see this problem. Then we have some getters, which we may not use here, and then we have the run method, which basically loads the sample UML file that we are going to create, and then calls the transformation and returns both the source and target. And if you remember here in the main file, in the main class, when we run from the command line, basically we call this method, then we get write. Write is the target model, source is test, and we save it. And then we can see the transform method, which will return a new target model on each run. And you will see later why we need to be able to run the transformation several times. Basically, it's for the test. So we create a new target model. We apply the transformation. So here, the transformation is not written yet. So this is why we have an error. But now that we have seen how it's going to be called, we kind of know what we have to write in this class. And it returns the model. And then the test starts by running the transformation, because basically what we want to test is change propagation, so we have to run the transformation at least once. And then we have several tests. One test, the first one here, is going to traverse the whole source model, looking for UML classes, and it will change their name and check that the propagation was successful. So we are going to see how this check is performed in a few seconds. So there are further tests like testing adding a class in the source model, testing adding a class in the target model, testing changing the names of target elements, testing setting abstract on the class to check of the source model to check forward propagation of something and so on. And then we have this check method. This check method actually what it does is rerun the transformation. This is why transform needs to return a new model each time it's called. And then it performs comparison. And here we did not reuse any fancy stuff like CMF compare or things like that, because we just need a very simple and fast. Because when I said we perform millions of changes for fuzzing, after each change we have to compare the models. So we have to make sure that it's efficient. But of course it's efficient, but the result is not very detailed. So basically the idea here is just to check if there is a difference. So all these methods perform the comparison. And if there is a difference, we kind of pinpoint it. But basically what the developer is expected to do is to write a test if it was discovered by the fuzzer, to write a test to check to make sure that and reproduce the test, and then using the main or another class, but a similar class, it can just run the transformation once by saving the resulting models and actually use fancy tools like EMF compare or other similar tools, which will help pinpointing the issue. But actually, this simple comparison code has been quite useful, and at least it's fast. So we're keeping it that way for the time being. And then there are some utility methods. For all contents, basically the method that simplifies traversal of the whole model contents and applying a consumer C to every element. On get all contents is just to get an iterator over the whole model contents. And so, as mentioned in the comment, we iterate over a copy of the resource contents, because if the test that we want to perform add some element to the model, we don't want the concurrent notification exception. So now that we have seen how the test framework works, we can have a look at how we are going to write our transformation. So we have to create the UML to eCore class. And we can use quick fixes to create what we need. So we have the source model, the target model, and the target meta model. And basically, as mentioned earlier, we are going to get the source model root element, which is actually a UML model. We are going to transform it. So to transform it, we are going to call a method that we are going to call model to e package. And the result is going to be an e package that we are going to add to the target module contents. We need to write the module to ePackage method. So this method needs to return an ePackage. I'm going to call this F and T for source and target, as in the examples. And for this, we are going to use for package instance factory get any package. So we can try to run our transformation, but before that, just need to create a source module. So we're going to do this right now before going any further. So here it's just, I did not mention, but it's just Eclipse Mars 1 modeling with EMF, with the Papyrus installed. So we can use Papyrus. We're going to create a UML module, which we're going to call sample. This is what is expected by our code. We are going to create a class diagram because this is basically what makes sense to transform to the core. And we can finish. So we just have to wait because somehow it takes some time to probably load the jars for the first time. So I will add a couple of classes. A couple of properties. At least for the time being, we are not going to look at much more complex models. If we have time to complete our transformation a bit more, we can do it, but it also depends on your expectations. So once we have a minimal example working, I will ask you to see if you have specific requests regarding what you want to see next. So now that we have the sample UML, we should be able to run our main class to test the basic functionality. So if we want to look at the core model, we should see a package with no name and no class because we have not written anything. So the first thing we want to do now is to bind the name of the two elements. So if you remember correctly, we have to use EMF factory in the property box. And here I can use name, but I can also use the package type. And I will bind this to the box for the source element. And now if I rerun my transformation, So did I run the transformation? I don't remember. Let me rerun it. I don't remember where I was. So the name is not. Yes, I have to click on the file. So the name now is copied. of course, I could also open the UML file. Well, actually, I could open it with the tree editor so that we see all the elements in a similar structure. Of course, because I don't have, if you remember, any test on propagation of the name of the package written yet, we are not going to try the test now. We are first going to write the transformation for classes. But of course, we could add the test as well. There are many ways to do it. But before going further, as you see, I will often need this kind of things. So maybe instead of ecore package.instance, I could just do ecore package and create small helper field, and similarly for the factory, so this is the AOF factory, and then I can simplify a bit my code. So now what we need to do is to do something similar for the contents of the module. So basically, we have to create a property box for the target element with its property classifiers, if I'm not mistaken. So here, instead of doing it like this, and potentially making the mistake of mistyping it, I can of course use the ecore package that get e-package e-classifiers, which is an alternative. And then I will bind this to that, of course, but to another expression which starts from the source element and gets the packaged element. So the source element is a module, but module inherits from package in UML, and so it inherits the packaged element features. But of course, here we do not have any missed error because, as I said earlier, we don't have actual static typing because in the EMF we don't have any static information about the type of packaged element. We are going to see later how we can improve this, but in the meantime, we know about this, so we know that we have to do something. And what we are going to do is to call the connect to operation, because this operation will keep a trace. And here we are going to transform a source element into a target element, so we want to keep a trace. So we collect from our module, our classifier, our packaged elements. So we need to call an operation packageable element to e-classifier, and we have to write this method. And this method will return an e-classifier for a packageable element. We have to write the code of this method, but before that, as you can see here, we do not have the typing information, so the compiler infers object. So right now I'm going to specify the generic typing manually, and I will show you later how we can improve over this, as I mentioned. But right now we need to solve this issue. basically create property box text as generic parameter that we can go and see. I can show you in the API. It takes the type of the element and the return type of the property accessor. So what we have is a model, and what we get with packaged elements is a set of packageable elements. Now that we have specified this generic typing, it works. So here, we want to create an e-classifier. But depending on the type, of course, we want to make different things. So if the source element is a UML class, I don't need Java class. I can simply shorter code. So if it's a class, then what I want to create is an e-class. So I need the eCore factory, and here I will do as earlier. ECore factory. We'll do this, and actually here I can replace my code. Yes, I see your comment, Christian. I'm just using simple stuff, but of course more powerful things like UML switch could definitely help. So, Ecore factory that create what I want to create is a class, an e-class. So, if now I try to execute my code and look at the result, I have two classes without name. So I will, sorry, switch to the wrong class. I will now copy this name binding. So because both model and package on one hand and class and packageable elements on the other hand are named elements, we could also try to factorize this in a method, but right now I'm just doing it by copy-paste. We're not trying to be very, very fancy, but just trying to show how we can build stuff. And now if I go back here, you can see that I have my two classes. So this is simple, but actually, if you look at the code to just do this, it's a bit verbal. But now the power comes with the propagation, so we are going to run our test and check what works and what doesn't work. So all our tests do work right now, because we don't have many tests, except one, the one that adds an e-class. And the reason is actually very simple, because our transformation has some bidirectional bindings, but never creates a UML class. It only creates e-classes. So of course, if you add an e-class in the target, nothing will happen. So here, what we have to do is do something similar to what we have seen to have bidirectional collect. We need to provide a reverse collector to have bidirectional collect too. And what we have to do here is to use the UML factory. And here again, I will create a helper attribute because I will need something similar. Okay. Create a class. And if now I run again my code, every test passes. So right now we have a very simple transformation, of course. We can complete it if we want. But we have a very simple transformation that does propagate changes. So of course I cannot show you in the editor here that it propagates changes because we have not run it as a plugin yet. And actually we are not going to do it because we have already seen how it can work with UML of facade and so on. It's a bit more work to get connected to this, but basically we have tested propagation using these tests. And actually, to make sure that these tests do work, we can try to play with them, either by changing them or by performing some other kind of tests. So let me just have a look at the list of things I had prepared. Yes. So if, for instance, now, instead of copying the names, I do something similar to what we did earlier in the slide, and try to change the name of the target element. So we can use collect. What we want to collect is, for instance, E plus the name. And so because here we have a box of strings, and strings are immutable, we don't need collect mutable. Even though the name of the package able element is mutable, we are not collecting over a box of mutable values. We are collecting we are collecting over a box of strings. So if now we try to execute the transformation, we can check that the E was added. And if we now run our tests, we can see that some tests did not work. So the first test that doesn't work is the test that checks name change. And the reason is that we have not written a reverse collector yet. So similarly to what we have seen in the slide, we can try to remove. So probably here what is required is typing, because here the Java compiler does not know the type. So here we have a packageable element to a string. And here we have to a string. And actually, yes, wait, because it's the name, we can just put declassifier and avoid this error. Okay, so now we can try to run again. And now the test, the reverse name change test does pass. And we can have a look at why this does not work. And basically the reason is that when the name was null, so we just add a class. So it created a class, and basically when it tries, so a class with a null name, and when it tries to propagate again, it gets null. And the reason that this does not work is that we have created a class here without applying the bindings. And for this to work, actually, with a framework like Facade, it's very easy because it's automatically done by the framework. The framework leads you into writing the transformation in such a way that the bindings can be applied bidirectionally. But here, the way we have written our transformation, there is systematically a source as argument and the target as return parameter. So we have no easy way to solve this. So right now, I think that I'm not going to solve this issue just yet. I prefer to show you how to get typing information in a much simpler way. Because I see the time is flowing, so I think that it's better to show you the most useful things, because actually solving the issue of the remaining test here is something that's better done by using a more powerful framework than just pure AOF. But at least you have seen that pure AOF is already quite capable. So I will just get 2 Java files from my previous preparation work, and I will show you what's inside. So in the UML file, basically, I have the UML package instance, and then for some, not all because I don't need everything, for some of the UML types, I have corresponding interfaces in which I have a class field which contains the meta class as an AOF meta class, which can be an EMF meta class or plain old Java meta class. Here, of course, it's EMF. And we also have properties like the name property of the named element as accessor functions. So actually, if I access this name property, I will get a function, a unary function, that takes a named element and returns a string encapsulated in an I1. So to get the accessor, I use this. On this cast is just to make sure that I can cast it into an I1 string, because by default it's an iBox of object. On this, of course, this code is really verbose, but actually would be very trivial to automatically generate. And what is very useful in this code is that instead of having just E attributes or E structural features in general, which are not generically typed, I get something that is generically typed not only with the source type, but also the target type. So if I use this, I should save some generic typewriting in my code. So you can see that I have done this for a couple more classes and features. And actually in the eCore file, what you have is basically the same thing for a few elements. And so if now I go in my code and I try to use this, for instance, here, well, let's go here because this is where we have these typing issues. So here I can use eCore dot ePackage dot eClassifiers. I apply it to P. And you see that now it types correctly because I have an eClassifiers property which is generically typed. So here I'm showing you in this simple context, but it's even more powerful with the collect mutable and other fancy AOF operations. So here I can do the same for the target, UML package dot packageable elements dot apply. I don't need to specify any generic typing in my code here. It's all in a separate Java file which can be trivially automatically generated, and I have something that's a bit more readable and easier to write. Of course, I can do it also for the name. One of the things that's interesting is that not only will it do the static checks for typos, which I actually already get by using UML package. Like for instance, here I could use UML package get named element theme, but it also makes it can also make the binding type checking, because here not only with this new approach here, not only do I get the name checked, the name of the feature, but I also get its type checked. Whereas here, what is written to me is just an E attribute, which does not inform the compiler about the type of elements it points to. So if I really want to do something complete, I can write ecor name, okay, dot apply t, and here we can do UML dot named element dot name dot apply s, and now not only it checks that the property exists, provided of course the ecor.java and UML.java file have been correctly written or generated. But if they are generated, we can rely on this, of course. But it also statically checks the type. So this is even more powerful. Of course, if we generate code from OCL, for instance, in the future, this may be less relevant. But in the current context, it's very useful to be able to write this kind of code that is at least partially checked statically by the Java compiler. So there are, of course, I could continue here, but you understand the idea. There are other things that we could do. Let me just have a look in my preparatory work. What did I try? Yes, I tried to use select, and select is able to show date and so on. But I think that we have already covered this in the slide, and it's probably time to wrap up now. So I will stop the demo now, wait a couple of minutes to see if we have questions, and resume to the slides for the wrap up.
Yeah, I have a question about the reverse adding an E class. We saw in the test, I think that when the test added the E class, the corresponding UML class was created on the source side, and it also got a name, but your reverse collector didn't bind any name. Was that binding somehow found automatically from something else?
Yes, that's a very good question. Actually, I suppose this is what you refer to, right?
Yeah.
So actually, the target class does not have a name, so it's null. And of course, if you reapplied this collector here, you would get E null. But I understand why you don't see how this happens, because it's not a trivial thing. Actually, what you see here on the left-hand side of this operator is what is computed by reapplying the transformation. So when we perform the check, basically what we do is we reapply the transformation on the new updated source model, and we compare the target models. And so what you see on the right is what happens when you apply this on a class which has a null name. Actually,
okay, yeah, that was what I missed, was that the test actually reapplied the forward transformation. Okay.
Yes. So actually, even if we correctly handle the binding setup here, because we only create the class and we do not create any binding for the reason that I explained earlier. Even if we did it, we would probably have a problem here because this is not written to handle a null value. So anyway, we would need to do something like if E is null, then probably we need to return something like this, or maybe like this, or I don't know, or something like that. But otherwise, it will fail.
Yeah.
So, okay. Thanks. So I will continue slowly, but if you have any other question on the UML to Echo transformation now or even after the webinar, of course you can contact me by email. Don't hesitate to interrupt me. So basically, what can we conclude? At least, what can I conclude? Maybe you may disagree, but for me, it shows that AOS without any framework is already quite powerful, even though it's a bit difficult to handle situations like reverse creation of elements if you have not written your code in the right way. For instance, as I mentioned, with a framework like Facade, basically, you write your bindings from source to target, but you use a helper method that will actually apply them in the right direction if you need to apply a reverse creation of elements. And you actually do this in a method that takes both the source and target element as argument, not a method that takes the source element as argument and returns the target element. So this is the kind of thing that when you write code like I just did, you don't necessarily think about before, but when you use a framework that like Facade that guides you to do it, so actually instead of just talking about it, maybe I can just do a quick, I can quickly show you how it works. I just need to find the right Eclipse, because I have so many, I think that's yes. So this is where I showed the Papyrus stereotype listener earlier. If I go to Facade, I can show you, for instance, the capsule. So there are many things here. There's model to model and class to capsule. So I will put this in full screen. So in this code, there are many comments here because I have made some tests. So maybe I should remove them, or maybe another example. Try to find an example in which I have not messed up the data. So, well, let's look for instance at this connector end. So we want to transform a UML connector end into UMLRT connector end. And here, these variables are basically similar to what I showed earlier. They are metaclasses and I have accessors and so on. They don't use the dot notation because at that time I was not using exactly the same layout for this kind of interface, but basically it's the same. And we can see that the command here basically uses the pseudocode that we have used in the slide. And on each binding, you see the same pseudocode as we did for more clarity. So basically, here, you specify that you add a new rule, and this rule has a source type, a target type. It also has a name, which can be used for debugging. And this rule has a bind contents method, which takes both the source and target element and a bindings helper. And basically, here, we have the special case when source and target property have the same name, so we don't need to repeat it. Here, we add the binding, and If we go in the forward direction, then we will have a new the source on a newly created target. So we will bind from source to target to initialize the target. But if we do it in the reverse, we will get an already initialized target, a newly created source, and the bindings object here, we know that it is being applied in the reverse direction. And so instead of initializing from source to target, or binding from source to target, it will bind from target to source, and then it will both handle the problem of actually creating bindings between source and target elements, even in the reverse direction, which we had an issue with in our UML3 core transformation. It will also handle the establishment of the binding in the right direction. So this is the kind of things that you can build in a framework to abstract over this, and which make the code that you write even simpler to write and understand. So this is basically what I have written here. More complex things require abstraction, and some of it can be built generically. I'm sure that although Christian developed his framework separately from Facade, as far as I know, he could reuse some things that are in Facade and vice versa. There are definitely some things that I have seen in his code that we could reuse. But there are also some things that are specific. Notably, if I go back to Christian's example, he has some complex retainment rules. Basically, he wants to stop propagating at a given time, depending on user interaction. And he wants to continue propagating some stuff in one direction, but not other stuff. And he can reopen the editor. And of course, when the editor is reopened, you have to remember these retainment rules. So all this kind of stuff, which may be more specific to a given case study, of course, may need to be tuned to specific problems. So there are several ways to debug and to test. I have shown you how you can write a test class. So actually, I have shown you through an already written test class because I just wanted to focus on the transformation. But you see how this can be done. But there is also this inspect pseudo operation, which is similar to the trace in Haskell, for instance, or to the debug in ATL. Basically, this kind of operation in functional languages that dump the value of their source to the console, but return the same value so that it has no side effect on the data flow. It has just a side effect for debugging. But actually, inspect goes a bit further than that, because inspect will tell you about changes. So if, for instance, on this I should be able to perform a quick demonstration if I find the right Eclipse. Yes, so this is the one in which we have written our transformation. If, for instance, I decide to inspect, so this is an accessor, so I have to inspect a box. If I decide to inspect the name of a class, of any class name, okay, and if I run normally, it should not do anything because I have disabled inspect. Yes, it does not open the console. But if I go there and enable inspection, I should see something. And you see here that the name, well, to have something that's a bit better, I should add space at least. We run it. So here you can see that the name is null and then is replaced by root element. So actually, I said e-class name, but I added it in the wrong method, so it's actually e-package name. So it's less interesting. So I will do it here. Further. And you can see here the e-classes getting their name. So they start being null before the bind is actually called, because inspect is called before bind. But once the bind propagates the change, you see that the value of the name is replaced. And actually, if we run the forward name change test, we should see that each class is originally named according to the corresponding domain class, and then it gets its name replaced. So this is just to show you that inspection can be useful, even if like every printf or system out println debugging approach, it's not scalable. It can still be used. Maybe connecting it to the logging framework would help. So there are also other possibilities for debugging. So I will show later that, well, I will show now that actually once you have built the whole data flow, which is basically an interconnection of operation boxes, you get complex stuff in memory, and that it's useful to be able to visualize it. So here it's just a screenshot, but actually you get a full view of the data flow. And you can even move your mouse over the various boxes and see a stack trace of their creation, so that you can make sure that the box you are looking at is really the box that was created in the method you have debugging. You can also serialize expressions, so this is especially useful when you are using the Eclipse debugger, because you can register specific serializers, so that instead of seeing basic Java object to string, you can see the actual code that is, at least the actual pseudocode that the given operation or box corresponds to. So testing, well, we have only looked at testing the active part, because actually testing the passive aspect of the transformation in AOF is no different than testing the transformation in general. So what I mean by passive aspect, I mean testing the transformation without change propagation, just testing that without propagation it does what you want. So you can do it in a traditional way, let's say. On testing a change propagation forward on reverse, actually requires specific approach, which I have shown in the practice. So basically you execute the transformation once, you perform some change on the source, you execute this propagation to the target, you execute the second time the transformation, and you compare the result to the result of the propagation to the result of the re-execution of the transformation. And of course, for the reverse, it would be better to follow the same scheme, except that you change, of course, the target instead of the source. But in some contexts, it may be interesting also to reverse propagate and to compare the two source models resulting from the reverse propagation and from the re-execution in the reverse side, if the transformation can be executed in both directions. There are other things that we could discuss, like rewriting. Basically, when you write OCL, it's much less verbose and much simpler than writing AOF, but it means that to generate AOF from OCL, we would need to perform some static analysis. For instance, collecting a complex navigation has to be rewritten into a chain of simple collections. And of course, there are complex things like if-then else on mutable condition inside of the collect, which require using this switch collect operation, which I mentioned earlier, which I can show in the Java doc. So I'm just showing the Java doc to show you that even if these things are not explained in details in the slides, of course you can have a look at the Java doc and also at the text, because basically the text have provide even more examples, even if they are a bit more complex to read than the Java doc. I wanted to go back to the slide, sorry. So, what are the perspectives for AOF? Well, there are many things to do, because, as I said earlier, AOF is a synchronization enabler, so it means that it opens new opportunities, but it also opens new problems that we did not have before because we could not get to having them. So, one of the things that we want to do, of course, is this rewriting. So first compiling simple OCL to AOF, but also more complex OCL expression rewriting. This also implies figuring out which subset of OCL, if not all of OCL, can be supported. About reverse change propagation, we would need also to automatically be able to derive reverse collectors, which is not always possible, so this is why I mentioned earlier that annotations may be necessary. Support for more operation would be useful. Closure, for instance, could be very interesting, again, in the UML context, for instance, if you wanted to do things like computing super classes in an observable way and so on. Expressions that are of the fourth form, if you remember one of the initial slides, which means that they don't have an equal operator that can be trivially transformed into a binding. Then for this we don't have clear ideas yet, but ideally we would like to be able to solve this. Again, performance has not been studied yet, but we know there are some things that we can do. But of course, before starting optimizing, we need to have a benchmark on Arcos suggested one, so we're going to look into that. And of course, there are some current limitations which have prototypes like predicate reversal, which are not mature yet, or that have even less mature prototypes like lazy evaluation would be interesting. So basically, lazy evaluation is the idea that you create the data flow when you evaluate the transformation, but you do not compute the actual values until they are requested. For instance, if you want to visualize a very complex and large model, most of the time you will only see on the screen at a given time a subset of it. So it does not make sense to generate a view for the whole big model. But by doing it lazily, you could achieve this without having to write your transformation in a complex way, because basically the framework will support lazy evaluation for you. One other thing that would be useful also to understand exactly what we can do and what we cannot do and why we cannot do it is to align the mutation-based semantics of AOF with functional lenses, which have formal semantics that have been studied for years, on which they have proofs not only of performance but also of feasibility or non-feasibility of some things. And finally, the idea of leveraging the upcoming version of OCL with pattern matching and shadow objects to simply write transformations in OCL. But if we do this with AOF, there would not only be functional transformations, but also incremental and possibly bidirectional transformation. So for me, that's the end of what I had prepared. If you have questions now, don't hesitate. You can go back to anything. And if you have questions later, again, don't hesitate.